Log on, tune in, find out. Another good idea from Cambridge.
So our first speaker for this morning is Tasos Sidiropoulos, who will speak about discrete differentiation, local rigidity of smooth sets in differential.
Should I finish by 11?
Say again?
Should I finish by 11?
Yes.
Great. So, can you hear me? Yeah. So this is joint work with James Lee. The topic of this talk is a lower bound for embedding into L1. So let me begin by some very simple definition of the main object we are going to be dealing with. So suppose that you have two metric spaces M and M prime. An embedding of the first space into the second one is simply a mapping that sends every point of the first space into a point of the second space. And the distortion is some parameter that quantifies the extent to which this mapping preserves the geometry of the original space. So in particular, the distortion is intuitively it tells how much the mapping stretches distances to fit the first space into the second. Okay, and then if the host space is some fixed y, we use the notation c sub y of x for the minimum possible distortion to embed x into y. Okay, and when y is some LP space, sometimes I'm gonna write C sub P instead of C sub L sub P. Sorry?
The distortion here is infinity.
Why?
C is a hour.
Yeah, that's a good point. But, so let's ignore this.
It's not the same hour.
Yeah, it's a different photo. Okay, yeah. So. Okay, so a doubling space. So the topic of the talk is a lower bound for embedding doubling spaces into L1. So let's define what a doubling space is. So a metric space is called doubling if for every r, every ball of radius r, so for example this blue ball, can be covered by a constant number of balls of half the radius. Okay, so these red balls here. And it's easy to see that this notion captures several interesting metric spaces. And what's nice about it is some completely metrical notion of what it means for a space to have bounded dimension. Okay, so let me very briefly remind you what's known about embedding into LP spaces. So it is known that every n-point finite metric space embeds into Euclidean space with logarithmic distortion. And in fact, this bound is best possible, for example, for the shortest path metric of the n-vertex constant degree expander graph. Now, for doubling metrics, the situation is slightly better. In particular, it has been shown that one can get distortion which depends on the square root of the logarithm of the number of points. And this bound is actually tight. So this slide, roughly speaking, says that doubling metrics exhibit some nice behavior when we want to embed them into LP spaces. Now, if we change the norm from L2 to L1, what happens in this slide is that this last line changes. So everything else remains the same, but we don't quite know what's the lower bound for embedding doubling spaces into L1. Okay, so the currently best known lower bound is log n to some fixed power. So delta is something tiny here. So there is a gap here. We don't know exactly what's the exponent. Okay? And so in this talk, we make progress towards closing this gap. In particular, we give a lower bound of square root of log n over log n, which, in other words, matches the upper bound up to a factor of square root of log n. Okay. So the main ingredients of the proof that I would like to highlight in this talk are more or less three. So the first one is that we actually construct a new family of doubling spaces on which we prove the lower bound. The second one is that we derive the lower bound via a differentiation argument. This is becoming a standard technique for bounds of this type. Although we have to use a slightly different version of it. And finally, we need to prove some isoperimetric property for sets on the plane that I will discuss later on. Okay, so let's start with the actual construction. So the first space we construct, we call the diamond fold for reasons that I will explain later. So the space is the following. So the diamond, it's a recursive construction. The diamond fold of order 0 is simply the unit square. Okay, now to construct the diamond fold of order 1, you simply take two unit squares and you identify their boundaries. Now in my picture here, it appears that these two squares bend, but this is only for clarity. Okay, these are just two flat squares with their boundaries identified. Okay, so topologically this space is homeomorphic to the sphere. Okay, now so in this space you can see that there are 8 scaled down copies of the unit square, okay, of length 1/2. So 4 on the top sheet and 4 on the bottom sheet. So in order to get the diamond fold of order 2, what you do is you take each one of these squares and you glue on it a copy of the diamond fold of order 1. Okay? And so on. Now in the diamond fold of order 2, you have 8 such squares, and you repeat the same process. Okay, is this clear?
The second, D2, repeat the starting.
So for D2, you look at D1. So in D1, you have 8 squares of side length 1/2. So you remove the interior of each one of these squares, and you glue on the boundary a copy of D1. Okay? So basically, you look at each one of these squares, and you double it. Right?
I don't quite see why the picture represents what you're doing.
Yeah, so the problem is that I cannot quite draw this object, so I'm just...
The D1 is just two squares making a little ravioli, yeah?
Exactly.
Ravioli loaf. Is that right?
Yeah.
Okay.
So ravioli is like a kind of pasta, right? Just to make sure.
But D1 is a polytope, just. D1 is a three-dimensional polytope, right?
No, so D1 is a two-dimensional simplicial complex.
Okay. But it can also be realized as the boundary of a three-dimensional polytope.
Topologically, yes, but not metrically. Yeah. Right. So this construction is reminiscent to something called the diamond graph, which is a one-dimensional analog of this object. So I forgot to draw this, so let me draw it on the board. So the diamond graph. So this is the object of order 0, just an edge, and then So the so the iteration is that you take every edge and you replace it by a cycle. Okay, so this is the object of order 1. So this is the object of order 2 and so on. And now you can observe that if you take the diamond fold of order k and you slice it along the diagonal, then the cross section is exactly the diamond graph. Okay, now this space is not quite doubling. The problem being that you can find arbitrarily large uniform metrics in this object. But you can make it doubling by a very simple trick, which is reminiscent to the construction of the Laxo graph, which pictorially looks like this. So I don't want to get to the actual details, but it's something fairly standard. And for the sake of simplicity, I'm just going to present the analysis for the diamond fold. But more or less the exact same argument goes through for the Laxo fold. Okay.
So the Laxo one, you really have a ravioli with real flat bits. Is that the idea?
I'm not really an expert on ravioli, but so what do you mean exactly?
So what is the difference with the Laxo one?
Oh, okay, yeah. So this region here is just one sheet.
Yeah. So it's really like a ravioli.
Yeah.
One. You have these flat bits that are around it. Yeah.
Yeah. Okay. So before I tell you more details about the proof, let me just introduce a piece of notation. So suppose that you have a finite set X, and you take a subset S. Then, with respect to this subset, you can define something called the cut pseudometric with respect to S, which I'm going to denote with this sub S here, which is a pseudometric in which every point that is either, for every pair of points, so that either both of them are in S or both of them are not in S, the distance is 0. And for pairs of points that cross S, the distance is 1. Okay, and we say that a distance function is the cut cone if it can be decomposed into a convex combination of cut pseudometrics. Okay, so this is the definition, and what's interesting for us here is that a metric embeds isometrically into L1 if and only if it is in the cut cone. Okay, this is a very simple but very useful fact for our purposes. So all this might seem kind of mysterious, so let me just give you, is there a question? So let me give you a very simple example. So suppose that you want to embed the end path into L1 using this cut cone representation. Okay, so one way to think of it is that you just pick a random number between 1 and -1, and then you partition the set of vertices into everything on the left of X and everything to the right of X. Okay, so this gives you a distribution over cuts, and in particular it gives you a convex combination over cut pseudometrics. Okay, you can check that the resulting embedding into L1 is an isometry. Perhaps another way to think of this is that, so this cut, so for any pair of points, the probability that the cut separates them is exactly proportional to their distance in the metric space. And this is why this is an isometry. Okay, and similarly, you can think about embedding the end cycle into L1, where you just take a line and you randomly rotate it. And this gives you, again, a random cut, and so on. Okay, this, I think, is a nice way to think about this setting here. Okay, so now the main technical ingredient that we need to use is something called differentiation for maps into L1. So this is a theory developed by Ziger Kleiner and refined by Lena Caventra. And so intuitively speaking, the main idea is to look at the mapping locally and argue that the cuts have to have a certain structure. And then use this structure combinatorially to prove some sort of lower bound. So let me try to make this idea a bit more clear. But before I tell you about differentiation into L1, I actually need to tell you about something called coarse differentiation, where the idea here is that you need to define some sort of differentiation for arbitrary metric spaces. Okay. So the way to do this, I mean, the main idea is the following. Okay, so suppose that you have an arbitrary metric space Y, and you have a mapping of the end path into Y. Okay, now, so the end path that I'm using here could really be any geodesic of some metric space, but let's just use the end path for demonstration. Okay, so we say that this mapping is epsilon efficient on this path if it satisfies the following condition. So what this says is that if you sum up all the distances along the path in the image, then this at most 1 plus epsilon times the distance between the endpoints. Sorry, this would be f of x1 and f of xn. Okay, and pictorially, the smaller the epsilon, the more straight the path has to look like. Okay. Now the extremely simple but extremely powerful idea here is more or less this. Okay. So suppose again that you have some host metric space Y and fix some distortion D. Okay, then for any arbitrarily small epsilon and for any arbitrarily large m, you can pick sufficiently large n such that for any mapping of the end path into Y with distortion at most D, you can find in the image of the path a copy of the path of length m, which is epsilon efficient. Okay, so this is probably difficult to parse in this form, so let me just draw a picture. So the proof is very simple. Okay, so let's fix m to be 3. Okay, so we are looking for a path of length 3, which is epsilon efficient. So let's see why this is true. So suppose that this is actually not true. So at every scale, any 3 path you can pick is not epsilon efficient. Okay. So this means that at the top scale, if you look at the first, the middle, and the last points, there has to be some kind of bend here. Okay, and then and then you can repeat the argument on each subpath here, and you see that the more you repeat the argument, the image of the path becomes more and more complicated. Okay, so it becomes longer and longer, and this gives you a contradiction on the distortion bound. Okay, so this is the idea of coarse differentiation. Now, how does this translate into maps into L1? Well, you need one more idea to make this idea useful for L1 maps. The idea is this. Okay, so suppose for the extreme case that you have a map of the end path into L1, which is 0 efficient. Okay, so the image of the path is completely straight. Then it is easy to see that all cuts in this cut cone representation of the L1 map have to be monotone. So by monotone, I mean here that each cut is induced by a half line. Now the point is that if you have a cut which is not monotone, then so pictorially this introduces some kind of bend in the path, so it cannot be straight. Okay, so this is extremely easy to check. So this is the situation in the one-dimensional case. Now in our case, we have a two-dimensional object. So we need to slightly modify the argument here. But again, at the high level, the idea is more or less the same. Okay, so we will argue that locally, the cuts induced by the cut cone representation have a certain monotone structure, where I'm going to define monotone more precisely in a bit. But this is more or less the main idea. Okay, so let's see what it means for a cut to be monotone in the two-dimensional case. So suppose that you have a map of the unit square into L1. Then differentiation tells us that there exists a sufficiently, if you look at a sufficiently small scale, you can find a square such that for every line that intersects this square, the mapping has to be efficient on this line. Okay, so in particular, from the one-dimensional considerations that I just described, this means that the cut has to be a half line on these lines. Okay, now if we look at the extreme case for just for demonstration, suppose that all cuts are half lines. So for every line, if you look at every cut, the restriction of the line is a half line. So this means geometrically that the cut has to be a half plane, because a half plane is the only set that satisfies this property. So suppose that we have this ideal case, and we can actually prove that all cuts are exactly half planes, which is not true, but let's just suppose it is for a moment. So then, if we go back to the diamond fault, by differentiation we can find two glued together unit squares, say these two, such that the so that the restriction of the cuts on both of them are half planes. Okay? But now what does this mean? So the key point here is that if you have two cuts, a cut in each one of these squares, and each of them is a half plane, then they have to be the same half plane. Okay? So this is the key point here. And the point is that the boundaries are identified, and the half plane is completely determined by its boundary. Okay? But now what this means is that in the L1 embedding, all cuts have to be identical in the top and the bottom sheet. But this means that metrically, the two sheets have to be collapsed. Does this make sense? Because, for example, if you look at a point at the top sheet and its copy on the bottom sheet, they are always on the same side of the cut. So they are separated with probability 0. So the distance in L1 is 0. Okay? Okay, so this is the main idea. Let me try to make this argument a bit more quantitative. Now, in order to make the argument more quantitative, there are a few obstacles we need to deal with. So first of all, we cannot really assume that the maps are zero efficient along lines. And the problem is that the minute you allow epsilon efficient maps, you might have no half plane cuts. This is in sharp contrast with the one-dimensional case where if you have an epsilon efficient map, you know that at least 1 minus epsilon fraction of the cuts have to be half lines. But in the two-dimensional case, things become a bit more complicated. And since we don't have a fixed line, we can consider to define epsilon efficiency, we need to define it actually with respect to a random line. And in order to avoid periodicities and things like that, we need to define it with respect to a random subset chosen on a random line. Okay, so more precisely, the actual technical thing one needs to prove is the following. So suppose that you have the unit square and a subset S in this unit square. Okay, so first we pick a random line, H, and then we pick a set of k points, uniformly at random, on this line. And we also add the first and the last, so the 2 points of the boundary, we also add them in the point set. Okay, so this gives us a sequence of points, and we define the complexity of a set to be the following thing. So we define C star of S to be the probability, so we take a random line and then a random set of points, and we count the expectation of how many times 2 consecutive points, one is in S and one is not in S. Okay, and we define this to be to be C star. Okay, and then we define C of S to be just the difference. So C of S is 1 if P0 is in S and Pk is not in S, or vice versa. Okay? And the point here is that these two quantities are equal exactly when S is a half plane. Okay, now the difficulty comes into actually bounding the difference between these two quantities. And the key step here involves proving that when the difference between these two quantities is small, then there is a half plane that approximates S, basically. At least inside this unit square. Okay, so this is the main geometric fact we need to prove. Let me just mention that this bound is actually tight. So we can prove that when the difference between the two complexities is epsilon square, the symmetric difference between S and some half plane is order of epsilon, and this bound can be shown to be actually tight. Okay, now given this quantitative bound on the complexity of a set, the argument is more or less similar to the ideal case of zero efficiency. So what one can argue is that, so first by differentiation, we find these two glued together sheets where maps are efficient, and via the previous geometric argument, we find a half plane that approximates both of them, okay? Which in particular implies that the restriction of the cut on the top sheet is close to the restriction of the cut on the bottom sheet. Okay, again, by the same argument, this implies that certain points of the top sheet have to be close to certain points of the bottom sheet, which gives you the distortion bound. Okay, so this is more or less the high-level idea of the proof. Are there any questions before I move on? Okay. So for the remainder of the talk, I would like to discuss some implications for the sparsity cut problem. So in the sparsity cut problem, we're given a graph G and capacities and demands between pairs of vertices. And for a cut S, we say that the sparsity of the cut is the total capacity crossing the cut divided by the total demand crossing the cut. Okay, and this, so computing a cut of minimum sparsity is a key step in several approximation algorithms. So approximating, in particular, the sparsity cut is a very important computational problem. And what is known about this problem is that so the first approximation algorithm was a log n approximation due to Leighton and Rao. The state of the art is approximation algorithm with so it's an algorithm of approximation guarantee squared log n times log n. And on the hardware side, it is known that there's no pitas basically for the problem. Okay, so before I get into the details of this approximation algorithm, let me just remind you some definitions. So we say that a metric space of negative type, if the square root of the distance embeds isometrically into L2, and similarly, let me say that it is of soft negative type if it embeds with constant distortion into L2. Okay, so the first log n approximation for sparsal scat was obtained by Leighton and Rao via a linear programming relaxation of the problem. And later on, it was realized that the LP relaxation, so the integrality gap of this LP relaxation is actually equal to the minimum distortion required to embed an endpoint metric space into L1. So in particular, by Bourgain's theorem, this statement recovers a slightly stronger, in fact, version of the Leighton-Rao algorithm. And the lower bound for embedding into L1 due to linear Lorenz-Rabinowitz tells, in particular, that the integrality gap of the LP relaxation is theta log n.
Maybe one should say that the first and last theorems were proved independently by Alman and Rabbani as well.
Yeah, thank you. Now moving on to the semi-definite programming relaxations. It says so. What is interesting is that there's again a geometric interpretation of the integrality gap. In particular, it is equal to the minimum distortion required to embed negative type metrics into L1. And in particular, the upper bound for approximating sparsal scat is essentially a geometric statement for embedding negative type metrics into L1 with distortion roughly squared log n. Okay, so unfortunately, it is not known what is the actual value of the integrality gap for sparsal scat. It's a major open question right now in the design of approximation algorithms, and it can be equivalently stated as a completely geometric statement. So in particular, it is not known what's the worst case distortion required to embed a negative type metric into L1. In fact, let me just mention that at some point it was conjectured that perhaps all negative type metrics embedded into L1 with constant distortion. And unfortunately, this statement was disproved by Cote-Bisnoy, who gave a super constant lower bound. And so the state of the art for this question is due to Leonauer. So Leonauer proved that the Heisenberg group endowed with the Carnot-Carnot metric is in fact a metric of negative type. And this combined with the result of Skerk, Kleiner, and Auer, who proved that the Heisenberg group requires distortion log to some constant to embed into L1, implies that the integrality gap for the SDP relaxation for sparsal scat is at least log to some constant power. Okay, and again there is this gap between the lower and the upper bound. This is similar to the case for doubling metrics. So what's interesting in the SDP relaxation for sparsal scat is that all known algorithms for sparsal scat in fact work even one optimizes only over metrics of soft negative type. So in particular, there's a apparently weaker relaxation, which, as far as we know, is as strong as the standard SDP relaxation for sparsal scat. And our result for embedding doubling matrix into L1, combined with the theorem of Fassoid, who proved that every doubling space is of soft negative type, implies in particular that so it implies the following corollary. So there exists a metric of soft negative type such that any embedding into L1 has distortion square root log n over log n. Okay, so just to rephrase this result, this implies that every analysis we know of for the sparsest cut SDP is tied up to a factor of log n. And to make it slightly more precise, so if this, so this is a standard SDP for sparsest cut. And if we look at a slightly weaker version of it, well, okay, some weaker version of it, then the integrality gap for this version is square root log n up to some log n factor. Let me just mention that the previous bound for the integrality gap of this weak SDP was log to 1/4 due to Lien-Mohanami. Okay, so let me just conclude with some open questions. Perhaps the most obvious question is closing the gap in what's known between negative type and L1. One way to do this would be to prove that the diamond fault embeds into negative type. But we don't know how to do this, and we suspect that it might not be true, but we don't know really. Another interesting point would be to see if these techniques can be used to somehow obtain harmonics of approximation for sparsest cut. It is conceivable that resolving this question, since this is exactly the question that one needs to resolve to establish the integrality gap for the sparsest cut SDP, it could be the case that that resolving this question is somehow a prerequisite for understanding the approximability of sparsest cut. But perhaps it could be the case that this construction tells you all you need to know. Okay, so this is just speculation, of course, but it might be worth trying to prove some hardness using these techniques. And finally, there is a very important open problem involving the embeddability of minor-free graph class into L1. So it has been conjectured that for any graph family that excludes a fixed minor, so this family can be embedded into L1 with constant distortion that depends on the minor. So, so in particular, this is not known even for planar graphs, if it is true or not, or for graphs of boundary width. So it seems that the diamond fault is similar to these graphs, but not quite, because it contains arbitrarily large minors. In particular, if you just take three grids and you identify them along on boundary path, this already gives you all minors. So it's not clear if one can perform this construction in this setting, but maybe it can tell us something about this question. So that's all.
Good questions. Yeah, so thanks again.